Welcome to the next set of video notes in the series and sequence unit. This one is called Series in Sigma. So our first question is, what is a series? So a series is the sum of the terms of a sequence. A sequence is an ordered list of numbers, as we saw in the last video. Please be careful not to use the words sequence and series interchangeably. Remember, a sequence is a list, and a series is a sum. There are two specific types of sequences and series that we look at, and these are relating to the length. There's finite sequences and series, and these have terms that can be counted individually from 1 to a final whole number n, so they end. And there's infinite series or sequences, and those ones continue without stopping. Today we're really only going to look at finite series, but know that infinite series are out there and they get kind of crazy. We'll look at them eventually. So the big thing today is this new notation called sigma notation. So we use sigma notation to express a series in compact form. The symbol for sigma notation is the uppercase sigma, this weird E thing. We read this expression here as the sum from n equals 1 to n equals 4 of 3n plus 2. Well, apparently I changed this to a 2 down here, so make that a 2. When written out as a series, you should see this expression right here. Okay, so you write it out, and each time you get a new term in the series, you're going to change n from the first value to the next integer value. So 1 right here, and then to 2, and then to 3, and then to 4. And that's going to give you the terms in your series. So we can do this right here. All right, so let's write out the terms of these series. This is the sum from n equals 1 to 6 of 2n plus 1. So I'm going to start by plugging in 1. Plug in 1 to this. 1 times 2 is 2, plus 1 is 3, so the first term is 3. 2 times 2 is 4, plus 1 is 5, so the next term is 5. And then I keep doing that. 7, 9, 11, 13. Okay. Now, I didn't actually plug those numbers in. Once I figured out the pattern, I was able to continue writing the pattern, but I stopped after getting 6 terms in the series because it only goes to 6. So just be careful and use your brain. Alright, this one's a little bit more complicated, so I might want to write it out. Start by plugging in 2. And notice how the letter here can change. Right, in this one it was N, this one it was I, it could also be K. Those are the different ones I'm going to use, but you could see really anything. I think I use R at some point. But just be careful. Be aware of what's going on. Make sure you read and don't assume. So this becomes 2 times 3 to the 1 minus 2, which is 1, plus 2 times 3 to the 3 minus 2, or 3 minus 1, which is 2, plus 2 times 3 to the 4 minus 1, which is going to be 3, and then my last term in my series is going to be 2 times 3 to the 4th. So you can see you went up by 1 in the exponent each time. And then if we go through and evaluate these, we see this is 6, this is 18, this is 54, and this is 162. Okay, to evaluate a series, all we're going to do is find the sum of the terms. So do the same thing you did before, write out each term, and then add them together to find the sum. So this one's a little bit different. It's not arithmetic or geometric, but we do the same thing. So we got 1 times 1 minus 3 plus 2 times 2 minus 3 plus 3 times 3 minus 3 plus 4 times 4 minus 3, and then last but not least is plus 5 times 5 minus 3. And each of these terms becomes negative 2, plus 0, plus 4, and plus 10. So I got 14 minus 4, this is just 10. Alright, next one. So this one, it's an interesting one. You see this negative 1 to the n. This is a common thing that could pop up in a series, and it does something relatively unique. Let's write it out, or at least the first couple terms. So I got 5 to the negative 1 to the 0 plus 5 times negative 1 to the first plus 5 times negative 1 to the second. All right, let's do one more, plus 5 times negative 1 to the third. Okay, well, each of these things is going to give me a different value. Right, negative 1 to the 0 is just 1, so this first term is just 5. Negative 1 to the first is negative 1, so I got minus 5. And then I got 5 times negative 1 squared. Well, negative 1 squared is positive 1, so that's just plus 5. And then this next one, unsurprisingly, is going to be negative 5. So they're going to alternate. Well, if you look at this, how many terms are going to be in this series? Well, 8 terms, because I got 7 plus the 0 term. That's 8 total, so I do plus 5, minus 5, plus 5, minus 5. And then you guys can see these will cancel out, and the sum is going to be 0. Alright, last one is as complicated as I can make them. Highly recommend when you see something like this, you plug it in to see what you get. Alright, so I got the sum from n equals 2 to 4 of this nasty expression here. Start with 2. So I got negative 2 to the 2 minus 1 divided by 2 squared plus negative 2 to the 3 minus 1 divided by 3 squared plus negative 2 to the 4 minus 1 divided by 4 squared. Okay, well, let's simplify the top and bottom of each of these. This becomes negative 2, because it's negative 2 to the first, which is just negative 2, divided by 4. And then I got, this becomes negative 2 squared, so 4 over 9. And then this one is negative 2 to the third, so negative 8 over 16. Alright. I notice that these are both actually 1/2, right here and right here, so this becomes negative 1, so it's really negative 1 plus 4/9, and that gives me negative 5/9 as my answer here. Alright, once you've figured out how to expand these things and write them out as a series, the real fun comes in putting it back into sigma notation. So let's look at a couple of examples with those. And this is really why we're doing this. This idea of pattern recognition and seeing what's going on is really, really important in mathematics, and this gives us some really nice practice on it. So this first one, if we want to write it in sigma notation, your first step is actually writing out the sigma. And this is the reason why you have a assignment that you're going to scan to me, because I need to see you guys getting practice writing these things. It's a weird notation. So I write my sigmas like that. I do it piecemeal. Sometimes I see people do this, and that's just not okay. That is not a sigma. It's not acceptable. You could do this. That's kind of acceptable, but not really. It's kind of more sideways M. Make sure you have those little line thingies at the ends. Be really careful when you make them. Okay, so once I got my sigma, I want to look and see, okay, how many terms are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 terms. So I'm going to start at 1, go up to 8. All right, now that I've done that, I want to look and see, well, what's the pattern? Looks like I'm going to be adding 3 each time. So if I'm adding 3 each time, that means it's arithmetic, which means I know the a sub nth term is going to be equal to 2, the first term, plus the common difference 3 times n minus 1. And if I simplify this, I end up with 3n minus 1. So that's what you're going to be putting here. The thing that goes here is the expression for the a sub nth term, the explicit formula for the sequence. Okay, and that gives us our sum. All right, this next one is a little bit more challenging because you can't count out how many things there are. But what we can do is we can create the a sub nth formula. Well, my pattern is just going to be adding 7 each time. So the first term is 1 plus 7 times n minus 1. All right, now that I've got this, I can simplify it. It becomes 7n minus 6 And then in order to figure out what n would be for the term 99, I'm going to plug 99 in for a sub n. So I got 99 equals 7n minus 6. Add 6 to both sides, I get 105, divide by 7. Oh, that's clearly n equals 15. Alright, now that I know n equals 15, and I know it's going to start at n equals 1, and I know my a sub n term, I can write my summation notation. Okay, this is going to be 15 up here. I'm going to start at n equals 1. Then we'll write the expression 7n minus 6. Okay. This one looks a little bit wacky, but I think we can put it together. Let's see what we're multiplying by each time. To go from 3 to negative 6, I'm going to multiply by negative 2. To go from negative 6 to 12, I'm going to multiply by negative 2. Okay, so this is geometric. So I want to write down the a sub nth term for a geometric sequence. Well, it's going to be your first term times your common ratio, which was negative 2, to the n minus 1. And then once we have that, all we have to do is look and see, well, if I know this expression, how many terms are there? There's 4, 5, 6, 7. There's 7 terms. So I'm going to write down my sigma, start at 1, go to 7, and then write down my expression for the a sub nth term. Oh, it wasn't so bad. Alright, now here's where they get complicated. This is really the fun part. There's going to be some hard problems on the worksheet that I made. Intentionally, there's some really difficult pattern recognition here. So I have 3 of them right here that's going on. Alright, so this one right here looks really weird. It doesn't even look like a sequence. It doesn't even look like there's a pattern. What's the rule with it? Well, I'm going to tell you guys, some of them are not going to be arithmetic or geometric because that's not fun. You have formulas for that. I want you guys to be working on your pattern recognition. So, when I look at this, I think to myself, okay, 1/2 plus 1/2 plus 3/8 plus 1/4 plus some things until I get to 7 128ths. Well, really what's happening here is after these initial 1/2s, I'm starting to get smaller and smaller and smaller. So how could I change these to make it look more patterny? Well, it'd be really nice if this was a 2 and this was a 4. So let's try that. Let's multiply the top and bottom of this one by 2 over 2. So I get 1/2 plus 2 over 4 plus 3 over 8 plus 4 over 16 plus ... plus 7 over 128. Okay, so I can kind of see what's going on now. The top is increasing by 1, and the bottom are powers of 2. And the thing that really clued me into this was that it was 2, 2, 8, 4, all of them have multiples of 2, and then that 128 all the way at the end. I know 2 to the 7th is 128, so that kind of gave me an idea of what was going on here. So if I had to write this in summation notation, my rule is going to be n on the top, and then on the bottom, it's going to be 2 to the n. So there's my rule. And then to write the sum, you just use your notation, start at 1, and go up to 7. And then write your rule. Okay, let's look at 11. Alright, this one, not as hard as the last one, and you can kind of see what's going on. What's happening each time? Well, each time I'm multiplying the coefficient by adding 2. So I'm adding 2 to the coefficient each time. Alright, all the way up to 20. So 2, 4, 6. And one of the things that can kind of help you with this is you can write down the terms of n. So n equals 1, 2, 3, and then this would be something up here. I don't know. I'll have to figure that out at some point. But if you know what n is, you can kind of figure out a pattern, right? If n is 1, how do you get 2? You multiply it by 2. If n is 2, how do you get 4? You multiply it by 2. Right? If n is 3, how do you get 6? You multiply it by 2. So my first expression is going to be 2n this gives me my coefficient. Now let's look and see what's happening to that exponent. I get x to the third, x to the sixth, x to the ninth. Each time I'm going to be adding 3, or 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9. So this exponent here is just going to be 3n. So this gives you your rule for the series. So now let's write it in summation notation. The question is, what's n? Well, if I look at this and I know that 2n is in front and the last term has a 20 in front, that means n has to be 10. So I start at n equals 1 and go to 10, and then I have 2n times x to the 3n. And that's my expression right there. All right, last one. And we're going to talk about something interesting here, so still pay attention. Okay, so I'm going to write my n's above again. 1, 2, 3, 4, 5, 6. Okay, well, here's an easy pattern. There's a little 1 right here. So the top is x to the whatever, right? So it's going to be x to the whatever, x to the 1, x to the 2, x to the 3, x to the 4, so on and so forth. And we have to be real careful with that, because notice there's also a negative in front. Okay, so with that negative, it becomes a little bit different. So we need to make sure we're doing the negative in front of it. So my expression here is going to be x to the n, and then in order to change things from negative to positive, you need to do -1 to some power. Okay, but if I do n and I plug in 1 here, it's going to be -1, which would make that first term negative. So what I do instead is I put a -1, because now when I plug in 1, I get -1 to the 0, and when I plug in 2, I get -1 to the first, which makes it negative. So that gives me the right step. Okay, so that's the top part. And then the bottom is going to be, well, should be 1 factorial if I continue the pattern, and then 0 factorial, because both 1 factorial and 0 factorial are 1. So now my pattern is that it's going to be 1 less than the n value. So it's going to be n minus 1 factorial. Okay. To write down the summation then, there's 6 terms, so I go from n equals 1 to 6 of this giant expression here. Okay, so this is your answer. Now there's something interesting that you can do with all series. So I like to start at n equals 1 because it keeps everything consistent for me, but you can also start at n equals 0. All right, so let's try that. Let's start at n equals 0 instead. So if I start with n equals 0, well, look at this first term. So I got x to the first divided by 0 factorial. And then know that I have a -1 in here as well, right? Well, if I just plugged in 0, well, all I need here is a 0. So I could just leave this exponent here as n, and I could leave the bottom as n factorial as well. But then what do I need to do to this exponent right here? Well, I got to add 1 to it, so it becomes x to the n plus 1. Right, so notice how these change. This is when it's equal to 0. Let me put this down too. And it's going to go up to 5 this time. So notice how this changes here. Notice how this becomes a +1 and these become n's. So if I add 1 to this n, I'm also adding 1 to my other n's to make them just n instead of n minus 1. And I can keep changing that. What if I make it n equals 2 down here where I start? Well, to generate this sequence with n equals 2, I'm going to go up to 7 to get my 5 terms. So I got n equals 2. Well, I need to do x to the n minus 1 to get that one right. And then I want this to be a positive right here. which I could really just leave it as x to the n, not x to the n, negative 1 to the n, and I would get something that works out with my alternating positive negatives there. And then on the bottom, it would need to be n minus 2 instead, factorial. So you can kind of shift it, and really if I put a minus 2 up here, it would work as well. And you can shift the value of n as you need, and it gets really interesting. And that's kind of why we have to narrow down where do you start with n, because it changes what the sequence is going to be if you don't say what it is. Thank you guys very much.